Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science. The topics is algorithms, and we were doing various algorithms for finding GCD or greatest common integer. Today we will be doing looking at the Euclid's algorithm. So today's content will be Euclid's algorithm, and then we will analyze the Euclid's algorithm and understand how good is it. And so the goal that we have is to find the GCD of two numbers p and q, positive integers, which is the greatest common divisor of two numbers. GCD is also known as the highest common factor or HCF. It is the largest number that divides both p and q. And in the last two lectures, we have seen a couple of algorithms. The first algorithm was what we called as the basic algorithm, which was basically writing down. So when we are given two numbers p and q, we know that the GCD of p and q must be some number less than or equal to p. So we write down an array A which contains all the numbers 1 to p, and we move from left to right from 1 to p, and if we find a I that divides both p and q, we mark that place in the array red, and finally we move from the right to left, that is from p to 1, and as soon as we see the first red, we output that. And we have seen that this algorithm does output the right value, and we also saw that the time complexity is exponential in the first input. Recall that the input size is the size of the input, which is p and q. Now p, when given in the binary form, requires only log p to the base 2 number of bits. So the size of p is log p to the base 2, and the time complexity or the number of steps in the algorithm that we just saw requires around 4p steps, which is exponential in p, in the size of the input, which is log p. So the time complexity is p, the input size is log p. And we also saw that the space complexity is also p, because we have to store the whole array which contain p elements, and thus it required exponential, which is again exponential in the input size, which is log p to the base 2. In the last lecture, we saw a better algorithm than that, in which instead of storing this whole array, we could only store a single variable temp, and as soon as we found an I that divided both p and q, we updated that value temp to I, and at the end the temp contained the GCD of the two numbers p and q, which we output. Again we saw that this algorithm does compute the GCD of two numbers correctly. The time complexity was again something like 4p, and the 4p was exponential in the input size of the first input, where the input size is log p to the base 2. But the space complexity had significantly improved. Instead of storing this whole array of p places, we could store only a single variable which was the temp, and thus the space complexity goes down to constant. In comparison, we had time complexity in the case of the first algorithm was exponential in input, which was also the same in the case of the second algorithm, which we called as Bether GCD. And in the space complexity regime, the basic GCD performed much worse. It had exponential in the first input, whereas the Bether GCD, the space complexity has become constant. Then the question was, can we make this improvement better, make this algorithm even better? And now one thing to note was that from going from basic algorithm, the first algorithm, to second algorithm, it was more of an implementation level improvement. Instead of storing the whole input, whole array of A, we are storing a single variable, and thus we got this space complexity improvement. But now to get the next time complexity improvement, we need to get to a better understanding of the number that we are trying to find out, which is GCD. And if we can do that, we can of course get a better algorithm. And to your surprise, the Bether algorithm is something that comes to us over 2000 years ago. It comes from Euclid, which is 300 BC, and we have to use a new trick for that. So first of all, let's revisit the properties of GCD. First of all, we had seen that GCD of P and Q is equals to GCD of Q and P. It doesn't matter in which ordering P and Q are given, the number that divides both P and Q will also divide the number that divides both Q and P. The second condition, if P divides Q, then GCD of P and Q is P. Again a simple observation this one, because P of course divides P and Q, and no other element greater than P will divide P. So GCD will be P. The third one was, if some other number T divides both P and Q, then T also divides the GCD of P and Q. We saw this one and the proof of this one in an earlier lecture, and in the last lecture we saw this property, which was that if I can write Q as some integer times P plus R, whatever that R is, whether it is less than P or not, doesn't matter, we can always say that GCD of P and Q is equals to GCD of R and P. We saw the proof of this particular property in the last lecture, and let's see how can we use this one to get a better algorithm. So for example, this is the property that we are talking about on top, and if you want to calculate the GCD of 12 and 44, say, we first write 44 as 12 times 3 plus 8. So remember, see that what we are doing is Q is 44, P is 12, 3 is the quotient and 8 is the remainder. Okay. Once we write it like this, by this property we have that GCD of 12 and 44 is GCD of 8 and 12, and again we can write 12 as 8 times 1 plus 4, and then again by this property we have GCD of 8 and 12 equals to GCD of 4 and 8, and then finally as 4 divides 8, so 4 must be equal to the GCD of 4 and 8, which is equal to GCD of 8 and 12, which is equal to GCD of 12 and 44. Thus we get the answer of 12 and 44 as 4. Notice the big improvement that has been happening is, to find the GCD of 12 and 44, we went down from 12 and 44 to 8 and 12, a reduction in the input, and from 8 and 12 we went down to 4 and 8, again a reduction in the input. In some sense, we are every step we are reducing our input or input size, whatever you want to call it. just to be sure we are in the same page, let us look at another example. So, we want to calculate the GCD of 14 and 33. Again 33 can be written as 14 into 2 plus 5. Now, therefore, GCD of 14 and 33 is equal to 5 and 14, and 14 can be written as 5 into 2 plus 4, and 5 can be written as 4 into 1 plus 1, and since 1 divides 4, so 1 is the GCD of 1 and 4, which is the GCD of 4 and 5. We are using this property here, right here, 4 and 5 is equals to 1 and 4, GCD of 5, and GCD of 4 and 5 is equals to GCD of 5 and 14 from this line, and GCD of 5 and 14 is equals to GCD of 14 and 33, just GCD of 14 and 33 is 1. Okay. So, here is the pseudocode of the whole algorithm. Pseudocode is just 4 lines and is very simple. What is it? So, if P divides Q, of course, we know that the GCD is P. So, we output P. The first part is kind of trivial. The second part is, if P is equals to P times D plus R, where R is strictly less than P. Note that we can always assume this thing happens, because we can think of dividing Q by P. So, D is the quotient, R is the remainder, and remember the remainder is always less than the value with which you are dividing, in this case is P. So, R is strictly less than P. So, R is in some sense the remainder when you divide Q by P, and then once we have that, by our property we know that GCD of P and Q is exactly equals to GCD of R and P, and thus all we need to do is call this function again with a smaller input R and P. So, it is like it is a recursive algorithm, an algorithm that calls itself again and again, but it calling itself with a smaller and smaller numbers. As such, the algorithm seems to be fine, but we need to prove a lot of things about this algorithm, right. For example, we need to first prove that the algorithm terminates, and remember that this is a recursive algorithm. So, if you have ever written a program in C or any other language, you realize that when you write a recursive program, the chance of it not terminating is high. There is a chance of not terminating. So, this particular proving requires some hard work. The second one is to prove that it outputs the right value. Then we have to understand its time complexity and its space complexity. So, let us start with this proof of termination. So, here is the pseudocode of the algorithm. Okay. Now, in the proof of termination, note that when we are calling Euclid GCD PQ, either P divides Q, and then the algorithm of course stops. It stops in the first round only. There is nothing to do with termination. It stops right there. Or we call a new function, correct? Not the new function, the old function only with a new input. We call which is the new instance, which is R and P. Now, every time we call with a strictly lesser input. And note that this R, that is in other words whatever value we call it with, must always be greater than 1. It cannot go down to 1, less than 1, correct? Because if R becomes 0, it means that P divides Q, in which case this part will kick in and we will output Q. So, R must be greater than or equal to 1, and first input goes down from P to R and is strictly less, R is strictly less than P, right, and thus the algorithm must terminate at some point. So, here what we are using is that we have an algorithm, a number that is slowly going down by a non-zero amount every time. So, the strictness says so, and it says that it cannot go down infinitely often, because there is a lower bound to it, which is R must always be greater than or equal to 1. So, it must terminate at some point, right. So, this proves that this algorithm terminates. So, the next thing to prove will be the correctness of the algorithm, but before that we will take a short break. We will come back and do the rest of the lecture. Welcome back after the break. So, now the next step to see is the correctness of this proof, and the correctness of this proof is again easy from the property, but let us first see the case that if P divides Q, then again we know that from the property of the GCD, then P must be the answer to this GCD of P and Q. So, if P divides Q, then GCD of P and Q is P. So, this part is right, and Q is equal to D times P plus R, where R is any number. In this case we have assumed that R is less than P, but it does not need to be. Then GCD of P and Q is GCD of R and P. This is the fourth property of GCD that we have seen, and thus when we output this GCD of R and P, under the assumption that this algorithm will also output the right value, our output of this whole algorithm will output the right value of P and Q. So, it is like a correctness of the bigger algorithm depends on the fact that the smaller algorithm is correct, and the smaller algorithm is correct because the smaller algorithm is just a baby version of the bigger algorithm. So, it is a bit convoluted argument possibly, but it is exactly how a recursive algorithm can be proved. The Euclid GCD P and Q, this algorithm will output the right value of GCD of P and Q, because the Euclid GCD P and Q will be calling Euclid GCD R and P, and GCD of P and Q is equals to GCD of R and P. Euclid GCD R and P will output the right value. So, GCD of P and Q will be the output of this whole algorithm. So, this is the proof of correctness of this algorithm. Now comes the interesting one. What is the running time of this algorithm? So, running time is something slightly more complicated to analyze, but if you remember the basic algorithm went for P steps. So, in the case of GCD of 12 and 44, we had to go for 12 steps one by one to see if I divides P and Q. In this case, we are making jumps from 12 and 44, we straight away went to GCD of 8 and 12. So, clearly our jumps are bigger than the earlier one, and hence we hope that this algorithm runs faster. Let us say we want to compute the GCD of P and Q. In that case, say Q is equals to P times D0 plus R0. Okay. Note that R0 is something that is strictly less than P. In that case, Euclid GCD PQ will call Euclid GCD R0P, right. Now, here if P is equals to R0 times D1 plus R1, then Euclid GCD R0 comma P, that will indirectly call Euclid GCD R1 comma R0. So, every time you are taking the first input to be the second input, and this first input becomes the remainder, right. So, this is how it will go. Now, let us see. In the first case, either this R0 is less than or equal to half of P, which is P by 2. In that case, R1, which is strictly less than R0, will be less than equal to P by 2. So, if R0, the first step itself, the remainder was less than P by 2, then R1, the remainder in the second case will be less than P by 2. Okay. If not, that means if R0 is not less than or equal to P by 2, then what happens? So in that case R0 is strictly more than P by 2. If R0 is strictly more than P by 2, then look at this second line here. What does it say? Then P must be equal to R0 times some integer plus R1. Now R0 is more than P by 2. So can D1 be equal to 2 or higher? No, because if I put D1 equals to 2, 2 times R0 is already greater than P. So this will become a negative integer, which is not good for us. So you must have got something like P must be equal to R0 times 1 plus R1. In other words, R1 would be equal to P minus R0. And now since R0 is strictly greater than P by 2, so P minus R0 will be strictly less than P by 2. Thus, in this first case also we have R0 is strictly less than P by 2. In the second case also we have R1 is strictly less than P by 2. Thus, in either of the cases R1 is strictly less than P by 2. So this is the catch, that after two calls, Euclid PQ calling Euclid R0P and then R0P calling R1 R0, P was the first input, R0 is the first input here. After two calls from P to R1, we have gone down by half. So after two recursive calls to the Euclid GCD, the input, I mean in this case I mean the first input, which is this first input to Euclid GCD, becomes less than half. So after two recursive calls, the input becomes half. So what happens after 4 recursive calls? So after 2 more recursive calls, the input, which was already halved, would have been even more halved. Or in other words, after 4 recursive calls, the input would have gone down even further, because it will be half, and after 4 recursive calls it will be half times half, which will be 4, right? And now if I keep on doing it, what does it mean? After 2 recursive calls it becomes half, after 4 recursive calls it becomes 1/4, after 6 recursive calls it will be 1/4 times half, which will be 1/8. Thus after 2 times log P base 2 many recursive calls, so every 2 recursive call it is halving. So what will be the input be? The input would have completely exhausted itself. So in fact this one, what is this one comes from? This is equals to 1 by, note that for every 2 recursive call it is halving, correct? So it will be 2 to the power of, like in this after 2 recursive calls it become half, so 1 by 2. After 4 recursive calls, 2 times 2 it becomes 1/4, is 1 by 2 times 2, or 1 by 2 square, and similarly here it will be 1 by log P base 2, which is 1 by P. So after 2 times log P base 2, the input becomes 1 by P of its original. And what was the original? The original was P. So this is equals to P times this quantity, which is P times this quantity, which is 1. So after the input becomes 1, the answer will be produced, because 1 will divide the other number, and in that case the algorithm will output 1 as a GCD. So what happens here? Either the two can happen, either in this, during this 2 times log P base 2 recursive calls, either we will be hit upon a place where the first input, or P in this case, will divide Q. The first input will be dividing the second input. In that case the output will be the first input and the algorithm will stop, or it will not stop, in which case a new call will be made, and after this many calls anyways the first input will become 1, and then the algorithm better output 1, because the 1 will always divide the next input. Okay. When the input is p and q, after 2 times log p many recursive calls, the input to the algorithm becomes 1. When the input is 1, the answer is produced immediately, because 1 divides the other one, and thus each of the calls requires 2 steps, right. So, the running time becomes at most, in fact this should be less than or equal to 4 times log p base 2. Why do I say it is less than or equal to? It is less than or equal to because it is possible that at some point in this whole process, the first variable will divide the second variable, and in which case the output will be produced immediately, else it will run for this many number of steps, rather this many number of steps, and in that case it will stop. So, the run time is less than 4 times log p base 2. The input size, recall the input size in binary is log p base 2, because this is the amount of bits I require to represent p, and similarly for q, log q base 2. So, input size is n plus m, this is what is usually noted, where this one is called n and this one is called m, and the run time now is 4 times log p, which is 4 times n. Recall that in the earlier algorithm that we had, what was the run time? The run time was something of the order, say 4 p instead of 4 log p, which was exponential in n or log p base 2. So, thus we have improved from an exponential run time to a linear running time. What about the space complexity? The space complexity is again constant, because all we need is some registers to maintain, there is nothing else to maintain here. So, we have got time complexity as linear and space complexity constant. Here are the comparisons of these 3 things. We have the time complexity, which is exponential in the case of basic, even in beta it was exponential, in the Euclid we have gone to linear, and it's a space complexity from exponential to constant, we jumped from basic to the beta algorithm, and for Euclid it is still constant. So, Euclid is significantly better than both of the other 2. Now, here one can ask some questions. Can one obtain a better algorithm than runtime linear? Is it that this runtime is linear because of the complex for the better analysis, or can a better analysis get a better than linear upper bound on the runtime? So, here I have a couple of questions that I would want to give you, because this kind of ends a module of 3 lectures that contains algorithms about numbers. So, if I give you a number n and I ask you, is that number prime? Design an algorithm for checking is that number a prime or not. Write down the pseudocode of it and analyze the runtime of it. The second question is, if I give you 2 n digit numbers and I ask you to multiply them, all of us have multiplied numbers in our high school and we know how to multiply numbers, but I want you to write an algorithm that will multiply these numbers and then try to understand the running time of this algorithm in terms of this number n, this which will be the size of the input. So, with this we end this talk, this lecture, and so in this today's lecture we saw Euclid's algorithm and we analyzed this algorithm and saw that Euclid's algorithm is significantly better than all the other 2 algorithms that we have seen. Thanks.